The date is December 27th, 2004. High above the Earth, in the silent, sterile vacuum of orbit, a fleet of scientific satellites are quietly doing their jobs. They are staring out into the cosmos, listening to the faint whispers of distant gamma-ray bursts and the steady pulses of spinning neutron stars. It is a quiet day in the solar system. And then, without any warning, an invisible tsunami of energy washes over our planet. For a tenth of a second, the universe seems to scream. It's not a sound anyone can hear, but a flash of light so powerful it overwhelms everything. Every gamma-ray satellite in orbit is instantly blinded. Their detectors, designed to catch faint flickers from across the universe, are completely saturated, their digital screens turning into a wall of pure, staticky white. The wave of energy is so intense it doesn't just hit the front of the satellites, it bounces off the moon and hits the back of them. Down on Earth, the wave of high-energy radiation slams into our planet's upper atmosphere. It rips atoms apart, creating a massive surge of ionization that measurably alters the shape and density of the ionosphere. For a few brief minutes, long-range radio communications on the planet's night side are disrupted. The entire protective magnetic bubble around our world visibly compresses and trembles from the impact. The most incredible part of this story is not that it happened, but where it came from. This was not an explosion from our own sun. This was not a supernova in a nearby star system. The source of this colossal wave of energy was an object on the other side of our own Milky Way galaxy, an object 50,000 light-years away. What in the universe could possibly be so powerful that it could physically affect our planet from a distance of 500 quadrillion kilometers? The culprit was a quiet, city-sized star, and it had just had a hiccup. It was a magnetar.
Tonight, we're going to take a slow, quiet journey to understand these incredible objects. We're going to explore the most extreme, most violent, and most magnetic titans in the entire cosmos. But this isn't a story to be afraid of. The terror of a magnetar is the terror of pure, unadulterated awe. It's the feeling of standing at the edge of the Grand Canyon and trying to comprehend its scale. Contemplating these objects can make our own world feel very safe, very calm, and very peaceful by comparison. So let's begin at the beginning. To understand where a magnetar comes from, we have to start with the death of a very large star. As we've discussed in other quiet stories, stars live in a constant state of balance. The inward crush of gravity is held at bay by the outward push of nuclear fusion in the star's core. For a star like our Sun, this is a very long and stable process. But for stars that are much more massive than our Sun, say 10 to 20 times as massive, life is much shorter and their death is infinitely more spectacular. For millions of years, these giant stars fuse hydrogen into helium. When the hydrogen in the core runs out, gravity squeezes, the core gets hotter, and it begins to fuse helium into carbon. This process continues, creating a series of concentric shells inside the star, like a cosmic onion. The outer layers are still fusing hydrogen, while deeper layers are fusing helium, then carbon into neon, neon into oxygen, and oxygen into silicon. Each stage of fusion is shorter and more frantic than the last. Finally, the star creates a core of pure iron, and iron is the end of the line. It is the final ash of stellar fusion. Fusing elements up to iron releases energy, which pushes against gravity. But fusing iron itself doesn't release energy, it consumes it. The moment the star's core becomes iron, the furnace goes out. The outward push vanishes in an instant, and gravity
which has been patiently waiting for this moment for millions of years, wins a sudden and catastrophic victory. In less than a second, the star's core, a ball of iron larger than the Earth, collapses under its own immense weight. The outer layers of the star begin to rain down upon it at nearly a quarter the speed of light. The core is crushed down past the density of an atomic nucleus, squeezing all its protons and electrons together to form a single, giant ball of pure neutrons. This newborn neutron star is incredibly dense and hard. The material falling from the outer layers slams into this new hard surface and rebounds, creating a shockwave of unimaginable power. This shockwave, supercharged with energy from a flood of ghostly particles called neutrinos, blasts outwards through the rest of the star, tearing it completely apart in a titanic explosion we call a core collapse supernova. For a few weeks, this single exploding star can outshine its entire galaxy. It is one of the most violent events in the universe, and in its heart, it leaves behind a tiny, city-sized, super-dense corpse, a neutron star. But for a magnetar to be born, something else is needed. The original star can't just be massive, it also has to be spinning very, very fast. And this is where the story gets truly extreme. The law of physics at play here is called the conservation of angular momentum. It's a principle you can see right here on Earth. Imagine an ice skater spinning in place with their arms stretched out. As they pull their arms in closer to their body, their spin gets dramatically faster. They haven't pushed off the ice again, they've just concentrated their mass into a smaller space. And so to conserve their angular momentum, they have to spin faster. Now apply that same principle to the collapsing core of a giant, rapidly spinning star. You have a core with the mass of our Sun, originally many thousands of kilometers across, collapsing down to a ball just 20 kilometers in diameter in a fraction of a second. The resulting spin-up is almost beyond comprehension. The newborn neutron star can be sent spinning hundreds of times every single second. This is where the magnetar's secret ingredient comes into play. In the first few seconds of its life, the newborn neutron star is not yet a solid object. It's an incredibly hot, dense soup of neutrons that is churning and convecting violently. So you have two key ingredients, incredibly rapid rotation and a turbulent, churning, electrically conductive fluid. This is the perfect recipe for a dynamo. A dynamo is a physical process that can convert motion energy into magnetic energy. It's the same principle that generates the Earth's magnetic field in its liquid iron core, but taken to an unimaginable extreme. This brief, violent dynamo moment in the heart of the dying star is thought to amplify the star's original magnetic field by a factor of trillions, creating the most powerful magnetic field in the entire universe. And with it, a magnetar is born.
So this process leaves behind one of the strangest and most extreme objects in all of creation. Let's take a quiet moment to appreciate what a magnetar, or any neutron star, actually is. First, there's its size and density. As we said, a typical magnetar is only about 20 to 25 kilometers in diameter. It's a stellar corpse the size of a city like Manhattan or London. But into that tiny space, it has packed the mass of 1.5 to 2 times our own Sun. The density is therefore almost impossible to put into words. A single teaspoon of magnetar material, if you could somehow bring it to Earth, would weigh about the same as Mount Everest. A sugar cube-sized piece would weigh more than all of humanity combined. The gravity
on the surface of a magnetar is hundreds of billions of times stronger than on Earth. If you were to drop something from a height of 1 meter, it would hit the surface in a microsecond, traveling at thousands of kilometers per hour. The object itself would be flattened into a 1-atom-thick layer on the surface. And what is that surface made of? We believe that a magnetar has a solid, crystalline crust, probably about a kilometer thick. It's made of iron nuclei and other heavy elements, locked into an incredibly strong metallic lattice by the intense pressure. It might just be the strongest material in the entire universe. Beneath this crust lies the bizarre interior. It's thought to be a vast ocean of neutrons existing in a superfluid state, meaning it flows with absolutely zero friction or viscosity. And deep in the very center, the pressure might be so great that the neutrons themselves are broken down into their constituent quarks, forming a mysterious state of matter known as quark-gluon plasma. It is a truly alien place.
But the defining feature of a magnetar, the thing that makes it what it is its magnetic field. And this is where our language and our analogies really start to fail us. The strength of a magnetic field is measured in units called Gauss, or sometimes Tesla. A typical refrigerator magnet might be about 50 Gauss. The Earth's magnetic field, which guides our compasses, is about half a Gauss. A powerful medical MRI machine can generate a field of about 30,000 Gauss. The strongest magnetic field we have ever been able to create in a laboratory on Earth is around 100,000 Gauss. The sunspots on our sun can have fields of a few thousand Gauss. A magnetar is on a completely different level. Its magnetic field can reach a strength of a quadrillion Gauss. That's a 1 followed by 15 zeros. It is 1,000 trillion times stronger than Earth's magnetic field. It is a force of nature so powerful it is difficult to describe its effects. Let's try. If a magnetar were to suddenly appear halfway to our moon, a distance of about 200,000 kilometers, the magnetic field would be strong enough to instantly wipe the data from every single credit card and hard drive on the entire planet. It would be a global, invisible magnetic catastrophe. Now imagine getting closer. Within a few thousand kilometers, the magnetic field would be so strong it would start to interfere with the human body itself. The electrical signals in your nervous system would be disrupted, and it would be instantly lethal. But the truly strange effects happen even closer still. Within about 1,000 kilometers, the magnetic field becomes strong enough to overwhelm the forces that hold atoms themselves together.
The electron shells that surround the nucleus of an atom are what give it its shape and allow it to bond with other atoms to form molecules. In the presence of a magnetar's field, these spherical electron clouds would be distorted and stretched into long, thin, needle-like shapes, all aligned with the magnetic field lines. In this environment, chemistry as we know it becomes impossible. Atoms can no longer bond in the familiar ways. Life, molecules, and even recognizable matter could not exist. Any object that got this close would be torn apart at a subatomic level, its atoms unraveled into thin cigars of plasma. And the final and perhaps strangest effect of this immense field happens to the vacuum of space itself. According to the theory of quantum electrodynamics, empty space is not truly empty, but is filled with a sea of constantly fluctuating virtual particles. A powerful enough magnetic field can actually interact with this quantum foam. It can polarize the vacuum itself. This means that empty space around a magnetar behaves like a crystal prism. If a beam of light passes through this region of space, it gets split into two separate polarized beams. This effect is called vacuum birefringence. It's a prediction of advanced physics that we have never been able to observe in a lab, but it should be happening constantly around every magnetar. The very fabric of empty space is altered by their presence. Surrounding the magnetar itself is its magnetosphere. This is not a neat, orderly magnetic field like the one around Earth. Because the field is so incredibly strong and twisted, the magnetosphere is a tangled, seething web of magnetic field lines, filled with a superheated plasma of electrons and positrons. This is where the action happens. This is the source of a magnetar's violent outbursts.
So we have this incredible object, a tiny, city-sized star with a magnetic field of almost unimaginable power. But for much of its life, a magnetar can be relatively quiet. The true terror of a magnetar comes from the fact that it is fundamentally unstable. Its enormous magnetic energy cannot be contained forever, and it releases this energy in some of the most violent events in the universe. The outbursts from a magnetar are not nuclear like a bomb, and they are not thermal like an explosion. They are purely magnetic in origin. The source of the outbursts lies in the relationship between the magnetar's solid, crystalline crust and the immense, shifting magnetic field that is locked within it. The internal magnetic field is so incredibly strong that it puts a constant, building stress on the solid crust, twisting and deforming it. The crust, while being perhaps the strongest material in the universe, can only take so much strain. Eventually, the magnetic stress becomes too great, and the crust suddenly cracks and shifts. This is a starquake. It's the exact same principle as an earthquake on Earth, where stress builds up along a fault line and is suddenly released. But on a magnetar, the scale is almost beyond comparison. A small starquake on a magnetar can release more energy in a fraction of a second than our sun does in an entire year. And these starquakes have a dramatic effect on the magnetic field outside the star. When the crust suddenly shifts, it drags the footpoints of the magnetic field lines that are anchored to it. This causes the entire tangled web of the magnetosphere to violently reconfigure itself. Magnetic field lines snap and reconnect in a new, simpler, lower energy state. And this process, called magnetic reconnection, releases a colossal amount of energy into the surrounding space. This energy takes the form of a giant flare of high-energy X-rays and gamma rays.
Magnetars exhibit a few different types of these outbursts. Most commonly, they produce short, relatively small bursts of soft gamma rays and X-rays. These are the events that led to them being classified as soft gamma repeaters, or SGRs. A typical magnetar might produce hundreds of these small bursts over a period of a few weeks or months during an active phase, before settling down again. These bursts are already incredibly powerful by human standards. But sometimes, something much, much bigger happens. On rare occasions, a major starquake can trigger a giant flare. These are events of a completely different magnitude. A magnetar giant flare is one of the most powerful explosions in the modern universe. In a fraction of a second, it can release more energy than our sun will in hundreds of thousands of years. We have only observed 3 of these events in our galaxy and its immediate neighbors in 50 years of watching the skies. The most recent and most powerful was the one we started our story with. Let's return to that day, December 27, 2004, and appreciate what we were seeing. The source of that blast was a magnetar known as SGR 180620. It's located about 50,000 light-years away from us on the far side of the Milky Way galaxy. For the flare's energy to have reached us and still been powerful enough to physically affect our own atmosphere from that incredible distance is just staggering. Let's try another analogy. Imagine the magnetar is a tiny glowing ember. Now imagine that ember is in the city of Tokyo. The flare it produced was so brilliant that if you were standing in New York City, that tiny ember in Tokyo would have briefly appeared as bright as a full moon in the sky. That is the scale of the energy we are talking about. It was the brightest event ever detected from beyond our own solar system, and it was just a hiccup from a city-sized star, a small cracking of its crust halfway across our galaxy. It is this potential for sudden, unpredictable, and mind-bogglingly violent releases of energy that makes magnetars so terrifying and so fascinating. They are quiet for years, and then, without warning, they can unleash a storm of radiation that can be felt across the galaxy. This brings up an interesting, if unsettling, thought. What if one were closer? The 2004 flare was from a magnetar 50,000 light-years away. At that distance, the effect on Earth was measurable but completely harmless. But what if a magnetar were to have a giant flare much closer to us, say, within a few hundred light-years? The consequences would be much more severe. A blast of gamma rays that intense could have a serious impact on our ozone layer, potentially causing damage that could affect life on the surface. Thankfully, we know of no magnetars that close to us. The universe is a very big place, and these objects are incredibly rare. There are likely only a handful of active magnetars in our entire galaxy at any given time, so this is not a danger to worry about. It is, like so many of these cosmic terrors, a thought experiment. It's a way to appreciate the raw power of the universe, and to appreciate the quiet, peaceful, and stable little corner of it that we happen to inhabit. The violence of a magnetar, when viewed from a safe distance, becomes a source of profound awe. Now that we understand what a magnetar is and the incredible events it can produce, let's move on to the next chapter in its life story. How do these violent objects evolve, and how do we even know they are there? One of the most surprising things about magnetars is that for all their incredible power, their lives are remarkably short. They are cosmic sprinters, not marathon runners.
The reason a magnetar's life is so brief is because of the very thing that makes it so special: its immense magnetic field. That field is a reservoir of an almost unimaginable amount of energy. But it is not perfectly stable. The magnetic field lines deep within the star are constantly shifting and trying to reach a simpler, lower energy configuration. This causes immense currents of charged particles to flow within the star's crust. These currents act like a giant, inefficient heating element. They generate a tremendous amount of heat, which then radiates away from the star's surface, mostly in the form of X-rays. This is why magnetars are actually much hotter than you would expect a neutron star of their age to be. All this radiated energy has to come from somewhere, and it comes directly from the energy of the magnetic field itself. So with every X-ray it emits, with every small burst and every giant flare, the magnetar is radiating away its own magnetic energy. It is, in a sense, bleeding its own power into space. This process means that over a period of about 10,000 years, a mere blink of an eye in cosmic terms, the magnetar's magnetic field will slowly decay. It will weaken from a quadrillion Gauss down to the normal trillion Gauss level of a regular radio pulsar. As the field weakens, the stresses on the crust lessen, and the star quakes and the violent outbursts become less and less frequent until they stop altogether. The short, violent life of the magnetar is over. It settles into a long, quiet retirement as a normal, much calmer neutron star.
destined to slowly cool and fade over billions of years. It's a spectacular but fleeting phase in the life of a stellar corpse. So, given that these objects are so rare and so distant, how do we even find them? How do we distinguish them from the millions of other neutron stars in our galaxy? The story of their discovery is a fascinating detective story in itself. It began in the late 1970s with the launch of new satellites capable of detecting gamma rays. These satellites started picking up strange, brief, repeated flashes of low energy or soft gamma rays. The sources were named soft gamma repeaters, or SGRs. This was a huge puzzle. The bursts were not like the known gamma ray bursts, which were single, powerful events from distant galaxies. These were weaker, and they repeated, with dozens or even hundreds of small bursts coming from the same point in the sky over a period of weeks or months. And on rare occasions, one of these sources would unleash a much more powerful giant flare. Scientists had found a new kind of celestial object, but they had no idea what it was. At the same time, astronomers studying X-rays were finding another class of strange objects. These were pulsars, spinning neutron stars that flash like lighthouses, but they were behaving oddly. They were spinning very slowly, typically rotating once every 5 to 12 seconds, which is much slower than a typical young radio pulsar. And yet, they were shining incredibly brightly in X-rays, far more brightly than their slow spin should allow, according to the standard theories of how pulsars work. Because of this strange behavior, they were given the name anomalous X-ray pulsars, or AXPs. For a long time, SGRs and AXPs were considered two separate, unrelated mysteries. No one knew what was powering either of them. The breakthrough came in the 1990s from two theoretical physicists, Robert Duncan and Christopher Thomson. They were the ones who proposed the Magnetar model. They suggested that both of these mysterious classes of objects, the soft gamma repeaters and the anomalous X-ray pulsars, were actually two sides of the same coin. They were both powered not by rotation like a normal pulsar, but by the decay of an ultra-powerful magnetic field. They had invented the concept of the Magnetar. Their theory perfectly explained the strange behaviors of both types of objects. The slow rotation of the AXPs was explained by the powerful magnetic field acting as a brake, slowing the star down very quickly after its birth. The intense X-ray brightness was explained by the heat generated as that magnetic field decayed, and the repeated bursts and giant flares from the SGRs were perfectly explained by their model of starquakes cracking the crust and causing the magnetic field to reconfigure itself. It was a beautiful, unifying theory. It took two separate astronomical puzzles and solved them both with a single, elegant, and admittedly terrifying new kind of object. Over the years, further observations have confirmed the Magnetar model spectacularly. We now know that SGRs and AXPs are indeed the same thing, just different observational manifestations of a magnetar's life. It was a triumph of theoretical physics, imagining an object more extreme than any we had ever seen, and then having that prediction confirmed by observation. But the Magnetar story had one more giant mystery to help us solve. To understand this next chapter, we have to talk about another of the great modern puzzles in astronomy: fast radio bursts, or FRBs. The story begins in 2007, when astronomers were looking through archival data from a radio telescope in Australia. They found something very strange. It was a single, incredibly powerful, incredibly brief burst of radio waves. It lasted for only a few milliseconds, a tiny fraction of a second. But in that brief moment,
It released as much energy as our sun does in an entire day. And when they calculated its distance, they found it came from a galaxy billions of light years away. This was the first discovery of a fast radio burst. Over the next decade, as our radio telescopes got better, we started finding more of them. They were popping off all over the sky, coming from distant galaxies. Some seemed to be one-off events, while others, called repeaters, would flash multiple times from the same location, but their origin was a complete mystery. What could possibly create such an intense, short-lived blast of radio energy? The theories ranged from merging black holes to, as is often the case, signals from advanced alien civilizations. For years, it was one of the biggest whodunit mysteries in cosmology. The problem was that all the FRBs we had detected were extragalactic, coming from so far away that it was impossible to pinpoint their source with enough precision to see what kind of object was making them. What astronomers really needed was to find one in our own backyard, an FRB that went off inside our own Milky Way galaxy, where we could get a much closer look. And in April of 2020, it happened.
On April 28, 2020, a Canadian radio telescope called CHIME, which is specially designed to scan the sky for these kinds of transient events, detected a powerful burst of radio waves. At the same time, another radio telescope array in the United States confirmed it. When they calculated its location, they realized it wasn't from a distant galaxy. It was coming from right here, inside our own Milky Way, only about 30,000 light years away. It was the first galactic FRB ever detected. This was the breakthrough everyone had been waiting for. Because it was so close, astronomers all over the world could immediately point their telescopes of all different kinds towards the source of the radio burst to see what was there. And what they found was definitive. The source of this powerful fast radio burst was a known magnetar, an object called SGR 1935 plus 2154. And at the exact same moment as the radio burst, our X-ray and gamma-ray telescopes in orbit detected a powerful X-ray burst coming from that same magnetar. This was the smoking gun. It was the first time a fast radio burst had ever been seen happening at the same time as an outburst from another type of object. It was the definitive link. This magnetar, in the midst of one of its active phases, had produced not just X-rays, but also a colossal, millisecond-long blast of radio waves. It was a moment of incredible scientific discovery, a puzzle piece snapping perfectly into place. It seems that our own galaxy's quiet titan had decided to solve one of astronomy's biggest mysteries for us.
Now, this single event doesn't necessarily mean that all fast radio bursts are caused by magnetars. There might be other ways to create them, but it provides a very, very compelling explanation for at least some, and perhaps most of them. It suggests that the thousands of FRBs we are now detecting from distant galaxies are the cosmic echoes of magnetars having violent starquakes and flares, just like the ones in our own galaxy. The radio burst itself is thought to be created as the initial blast of energy from the flare plows through the dense magnetized plasma surrounding the magnetar, creating a powerful shockwave that generates intense radio emissions. It's a beautifully complete picture. The quiet, strange objects we once called soft gamma repeaters and anomalous X-ray pulsars, which we unified under the theory of magnetars, have now also been shown to be the source of these mysterious fast radio bursts. It's a wonderful example of how science works, with different, seemingly unrelated mysteries slowly converging into a single, coherent, and awe-inspiring explanation. And so, we've explored the life of a magnetar, from its violent birth in a supernova
to its bizarre and extreme anatomy, to its powerful, world-shaking outbursts, and its eventual quiet decay. We've seen how our understanding of these objects has grown over time, from a collection of strange, unexplained observations into a unified and beautiful theory. This brings us to the final part of our quiet journey tonight. Let's take a moment for a final reflection.
The Magnetar is a powerful reminder that the universe is capable of creating objects and producing forces that are far, far beyond our everyday human experience. Our lives are lived in a very gentle, very calm, and very forgiving corner of the cosmos. We are used to a certain scale of things. A Magnetar completely shatters that scale. It operates at a level of density, gravity, and magnetism that is so extreme, our language and our imagination can barely find purchase. It is, in a way, a natural cosmic laboratory. It's a place where the laws of physics are pushed to their absolute limits. It's a place where the vacuum of space itself behaves in strange ways, where matter is crushed into forms we can only dream of creating on Earth. By studying these objects from a safe distance, by capturing the faint X-rays and gamma rays from their distant tantrums, we can test the boundaries of our own understanding of general relativity and quantum mechanics. They are a gift to science, a natural experiment of unimaginable proportions. And this brings me to the idea of terror versus awe. The physics of a Magnetar, if you think about it too closely, are terrifying. The idea of matter being unraveled, of a magnetic field that can kill from thousands of kilometers away, of an explosion so powerful it can be felt across the galaxy, these are not comforting thoughts. But the key, the thing that transforms that terror into pure, unadulterated wonder, is distance. Because these objects are so incredibly far away, they pose no threat to us. They are not our monsters. They are abstract, beautiful, and profound concepts. Their terrifying power, when viewed through the lens of immense distance, becomes a source of deep and quiet awe. It's a reminder of the raw, untamed power of the universe, but a power that is happening over there, leaving us safe in our peaceful little harbor.
And I find that profoundly calming. To contemplate an object so extreme is to put our own earthly worries into a new and powerful perspective. The little anxieties and stresses of our daily lives seem to shrink and fade away when compared to the fury of a starquake on a neutron star 50,000 light-years away. The Magnetar is a beautiful and violent part of the grand, complex cosmic ecosystem. Stars are born, they live, they die, and they leave behind strange and wonderful corpses. Some become quiet white dwarfs, some become pulsing neutron stars, and a very, very few, the ones born in just the right way, become these magnificent, short-lived magnetic titans. They are a fleeting but spectacular part of the universe's long story. So as you settle into your final moments before sleep tonight, let your mind hold on to that feeling of quiet awe. Think of that tiny, city-sized star with a heart of crushed atoms and a magnetic field that could warp reality itself. Think of its silent, patient waiting and its sudden, brilliant flashes of light. And let the sheer scale of it all be a soothing presence,
a quiet reminder of the incredible, strange, and beautiful universe you're a part of. From our safe and peaceful corner of the galaxy, we can look out at these cosmic monsters and see them not as terrors, but as wonders. Sweet dreams.
Let's linger for a moment longer on the birth of a magnetar. We talked about the supernova, that titanic explosion that signals the death of a massive star, but the creation of a magnetar requires that we look even more closely at the final chaotic moments of that collapse. Imagine that giant star with its onion-like layers of fusion. When the iron core collapses, it does so with incredible speed. A mass larger than our sun is crushed down to the size of a city in less than a second. This collapse is not perfectly symmetrical. It's a messy, turbulent event. The material doesn't just fall straight in, it churns and boils. Now add in the rapid rotation we talked about. The combination of this rapid spin and the churning, convective motion of the super-dense neutron soup creates the perfect conditions for that dynamo effect. Think of it like a cosmic blender of unimaginable power. The magnetic field lines that were present in the original star get caught up in this churning, spinning chaos. They get twisted, stretched, and folded over on themselves again and again, amplifying their strength with each rotation. This process is incredibly efficient, but it only lasts for a few seconds. After the initial collapse, the newborn neutron star begins to cool and solidify, and the violent churning motions cease. The dynamo turns off. So a magnetar has to be born with its colossal magnetic field already in place. It emerges from the supernova fully formed, a magnetic monster from birth. This is why they are thought to be so rare. You need to start with a star that is not only massive enough to go supernova, but also spinning at just the right, incredibly rapid rate. It's a specific recipe for creating an extreme object.
Now, let's go back to the anatomy of the magnetar, specifically its crust. We said it might be the strongest material in the universe, and that's because of the immense pressure it's under. The gravity is so strong that it crushes the iron atoms into a near-perfect, ultra-dense crystalline lattice. But this crust is also very brittle, and the magnetic field that is locked into this crust is constantly trying to move, creating immense strain. Imagine a tectonic plate on Earth building up stress along a fault line. Now imagine that stress is not from the slow movement of continents, but from a magnetic field a quadrillion times stronger than Earth's. The amount of stored energy in the magnetar's crust is colossal. This is why a starquake can be so powerful. A tiny shift in the crust, a crack only a few centimeters deep, can release an amount of energy that dwarfs our comprehension. And the starquakes themselves would likely create seismic waves that would reverberate around the entire tiny star. So not only is the magnetar blasting out energy into space, but it is also likely ringing like a bell with these incredibly powerful vibrations. Furthermore, the magnetic field has a strange effect on the crust's thermal properties. It acts as an insulator, channeling the heat from the star's interior out through specific hotspots on the surface, usually at the magnetic poles. So a magnetar's surface is not uniformly hot. It has incredibly hot polar caps and a relatively cooler equatorial region. This focused heating is another reason why they are so bright in X-rays. It's a complex and dynamic environment, a tiny world under constant, unimaginable stress.
Let's talk more about that 2004 giant flare from SGR 1806-20. The initial flash of gamma rays, the part that saturated all our satellites, lasted only about 1/10 of a second, but it was followed by a long, pulsating tail of X-rays that lasted for several minutes. As the magnetar's magnetosphere settled down after the initial violent reconnection, it continued to release energy in a series of rapid pulses tied to the star's rotation. The star was spinning once every 7.5 seconds, and the X-ray pulses arrived with that exact same rhythm. It was the ringing of the star after the main event, a clear fingerprint that connected the flare to a spinning neutron star. The total energy released in that flare was estimated to be about 10 to the power of 46 ergs. That's a number so large it's hard to find a good analogy for it. Let's try. If you were to collect every single bit of energy our sun will produce over its entire 10 billion year lifespan, the 2004 Magnetar flare released about 1,000th of that total energy in a single second. It is a level of power that is truly cosmic in scale. And to think, this was from an object on the other side of our galaxy. It's a humbling thought that the universe is routinely producing explosions of this magnitude. It gives us a deep appreciation for the quiet stability of our own solar system. We live in a calm, peaceful harbor, and the great storms of the cosmic ocean are, for the most part, very, very far away. This distance is what allows us to study these events with scientific curiosity and awe, rather than with fear. It's a perspective that I find deeply calming.
Let's delve a little deeper into the mystery of fast radio bursts and the Magnetar connection. As we said, the breakthrough came in 2020, when we saw a Magnetar in our own galaxy produce an FRB. But the story is even more interesting than that. The FRB produced by that galactic Magnetar was powerful, but it was actually hundreds of times weaker than the typical FRBs we see coming from other galaxies. This suggests a couple of possibilities. One is that our galactic Magnetar's burst was just a weak one, and that it is capable of producing much more powerful FRBs that are more in line with what we see from other galaxies. It might just be that the most powerful flares are much rarer. Another, more intriguing possibility is that there might be more than one way to make an FRB. Perhaps Magnetars are responsible for some, or even most of them, but there might be other, even more exotic cosmic events that can also produce these millisecond-long blasts of radio waves. The mystery is not entirely solved, which makes it even more fascinating. The study of FRBs is one of the newest and most exciting fields in astronomy. We're building new radio telescopes, like CHIME in Canada, that are specifically designed to scan the sky and catch these fleeting signals. Each new FRB we detect is another clue. By studying their properties and pinpointing their host galaxies, we are slowly piecing together the puzzle. It's a wonderful example of science in action, a global effort to understand a strange new phenomenon. And it's incredible to think that magnetars, these quiet, supermagnetic titans, are a key part of that story.
Now let's return to the anatomy of these objects and consider their final state. We said that after about 10,000 years, a magnetar's magnetic field decays, and it becomes a regular neutron star. What does that mean? It would likely cool down significantly, its X-ray brightness would fade, and the starquakes would cease. It might become a radio pulsar, with its now weaker magnetic field still producing beams of radio waves from its poles. Or it might just become a dead neutron star, a small, dark, quiet cinder, incredibly dense but emitting very little radiation, making it almost impossible to detect. The galaxy is likely filled with these older, dead magnetars, these quiet ghosts. They are the remnants of a short, spectacular, and violent youth. This short lifespan is another reason why magnetars are so rare. Not only is the birth process very specific, but the object itself only remains in its magnetar phase for a cosmic moment. we have to be looking at the right time to catch one in its active, noisy period. This brings up a fascinating thought. Are there other classes of extreme, short-lived objects in the universe that we haven't discovered yet? Are there other types of stellar corpses with bizarre properties that only last for a few thousand years? It's entirely possible. The universe is a vast and creative place. Every time we build a new kind of telescope that looks at the sky in a new way, we discover things we never expected. The story of the Magnetar is a perfect example of this. We first saw their ghostly gamma-ray flickers, then their strange X-ray glow, and now their fleeting radio shouts. Each new window we open on the universe reveals another layer of its complexity and wonder.
Let's take a moment to reflect on the name itself, Magnetar. It was coined by Robert Duncan and Christopher Thompson in their 1992 paper that first proposed the theory. It's a simple combination of magnetic star, but it has a wonderful, powerful ring to it. It sounds like something out of a comic book. And in a way, it is. It's an object with superpowers, a thing whose properties are so far beyond our normal experience that it feels like fiction. But they are real. They are out there, and our ability to understand them is a testament to the power of the human mind. Think about it. We have never been to a magnetar. We have never directly sampled its material. Everything we know about them comes from detecting faint particles in light, X-rays, gamma rays, and radio waves that have traveled across thousands of light years of empty space to reach our detectors. From those faint signals, by applying the laws of physics that we have discovered here on Earth, we have been able to construct a detailed, consistent, and beautiful picture of these incredible objects. We have been able to deduce their size, their density, their spin rate, and the unimaginable strength of their magnetic fields. We have been able to build a convincing story of their birth in fire and their slow decay into quiet darkness. It's an act of cosmic detective work on the grandest possible scale. It is, I think, one of the most awe-inspiring achievements of science. It's a quiet reminder that even though we are small and confined to one tiny planet, our minds are capable of reaching out and comprehending the most extreme and distant corners of the cosmos.
Let's think again about the starquake. The idea of a solid crust cracking under magnetic stress is a powerful one. On Earth, earthquakes are caused by the slow, grinding movement of tectonic plates. A large earthquake can release a tremendous amount of energy, enough to level cities. But a magnetar starquake is on a completely different level. The energy release is many, many orders of magnitude greater. What is perhaps most amazing is the scale of the crack itself. Because the gravity on a neutron star is so immense, the mountains on its surface are thought to be only a few centimeters high at most. Any larger structure would be instantly flattened by the gravity. So, a catastrophic starquake that rearranges the entire magnetosphere might be caused by a crack in the crust that is only a few meters long and a few centimeters deep. It's a strange paradox. A tiny, almost insignificant physical event, a small crack on a city-sized star, can unleash a blast of energy so powerful it can be detected across the galaxy. It's a lesson in the incredible energy density of these objects. Every cubic centimeter of a magnetar is packed with more energy than a fleet of aircraft carriers. So even a small disturbance can have enormous consequences. It's a quiet thought that reminds us how different the physics of these extreme environments are from our own. It's a world where the rules are the same, but the numbers are turned up to a level that is almost impossible to imagine.
Let's return to the idea of the birefringent vacuum around a magnetar. This is one of those concepts that sounds like pure science fiction, but it is a direct prediction of quantum electrodynamics, or QED, our theory of how light and matter interact. The theory says that the vacuum of space isn't truly empty, but is filled with a sea of virtual particle-antiparticle pairs that pop into and out of existence for fleeting moments. Normally, these particles have no measurable effect, but in the presence of an incredibly strong magnetic field, these virtual particles are forced to line up along the magnetic field lines. This alignment makes the vacuum itself behave like a polarizing crystal. So if a beam of unpolarized light, like the light from a distant star, were to pass through the magnetosphere of a magnetar, it would be split into two separate beams, each with a different polarization. In 2016, astronomers believe they saw the first evidence of this incredible effect. While observing a neutron star, not a magnetar, but one with a very strong magnetic field, they noticed a strange pattern in the X-rays coming from it. The pattern was consistent with the light having passed through a region of birefringent vacuum. It was the first tentative observational proof of this bizarre quantum effect. It means the very fabric of space-time is not immune to the influence of these magnetic titans. They don't just affect matter, they change the nature of empty space itself. It's a deep and profoundly strange idea, a quiet peek into the fundamental workings of reality.
As we near the end of our deep dive, let's consider the population of these objects. How many are out there? As we've said, they are incredibly rare. The conditions for their birth, a massive star that is also spinning incredibly fast, are not common. Scientists estimate that perhaps 1 in every 10 supernova explosions results in a neutron star. And of those, perhaps only 1 in 10 has the right conditions to become a magnetar. This means that for every 1 magnetar born, there are about 99 other, more normal neutron stars and pulsars created. Given these numbers, astronomers estimate there are probably about 30 million neutron stars in our Milky Way galaxy. But of those, only a very small fraction would be young, active magnetars. The current estimate is that there are likely only a few dozen active magnetars in our entire galaxy at any given time. We have, to date, identified just over 30 confirmed or candidate magnetars. So they are the rarest of the rare. But the galaxy is also filled with their corpses. Since a magnetar's active life is only about 10,000 years, and stars have been dying for billions of years, there should be millions of dead magnetars, now just quiet neutron stars, drifting silently through the galaxy. These are the quiet ghosts of past violence, their magnetic fields having long since decayed. They are a hidden population, a reminder that the sky was once filled with even more of these powerful beacons than it is today. The universe is slowly, very slowly, becoming a quieter place. Let's now return to our final reflection. We've journeyed through the entire life story of one of the universe's most extreme creations. We've seen its fiery birth in the heart of a supernova. We've contemplated its mind-bending anatomy. We've witnessed its spectacularly violent outbursts, and we've followed its slow, quiet decay into a common stellar corpse. We've seen how the patient work of science, of observing faint flickers of light from across the galaxy, has allowed us to piece together this incredible and coherent story. The Magnetar is a beautiful lesson in cosmic perspective. It is an object of almost unimaginable violence. The energies involved are so far beyond our human scale that they defy easy analogies. And yet, because of the immense cushioning distances of space, this violence poses no threat to us. It is transformed by distance into a subject of pure scientific wonder. It is a monster that we can study safely from our quiet harbor, a titan whose roars are just faint whispers by the time they reach us. And this, I think, is a deeply calming thought. It allows us to appreciate the power and the fury of the universe without feeling personally threatened by it. We can contemplate the starquake on the crust of a neutron star, the giant flare of gamma rays, the tearing apart of atoms in an immense magnetic field, all from a position of perfect safety. It is like reading a terrifying story while curled up comfortably in a warm bed. The thrill of the idea is separated from any real danger. It allows for a kind of intellectual and emotional tourism, a visit to the most extreme environments in the universe, all from the quiet stillness of your own room.
The Magnetar also teaches us about the interconnectedness of the cosmos. The story of magnetars turned out to be the story of soft gamma repeaters and anomalous X-ray pulsars, and even, it seems, of fast radio bursts. All these separate, mysterious phenomena were likely different faces of the same underlying object. It's a recurring theme in science. The universe loves to be efficient. It often uses one incredible type of object to create a whole host of different signals. It's a quiet reminder that all the strange whispers and flickers we see in the sky are part of one grand, interconnected story. And it reminds us that the universe is still full of surprises. We only really figured out what magnetars were in the 1990s. We only linked them to fast radio bursts in 2020. What other extreme objects are out there, waiting to be discovered? What other quiet whispers are we currently hearing but not yet understanding? The universe is not a static, solved puzzle. It is a living, dynamic mystery that is constantly revealing new layers of its complexity to us, as long as we have the patience to keep looking. So as you settle into your final moments before sleep tonight, let your mind hold on to that feeling of quiet awe. Think of that tiny, city-sized star with a heart of crushed atoms and a magnetic field that could warp reality itself. Think of its short, spectacular life and its long, quiet retirement. Let the sheer scale of it all be a soothing presence, a quiet reminder of the incredible, strange, and beautiful universe you are a part of. From our safe and peaceful corner of the galaxy, we can look out at these cosmic titans and see them not as terrors, but as wonders.
Contemplating an object like a magnetar does something wonderful for the human mind, I think. It stretches it. It forces us to think on scales that are not meant for our everyday brains. And in that stretching, there is a kind of peace. The small, immediate worries of our own lives, the deadlines, the anxieties, the regrets, can feel so heavy and so important. But when you place them next to the concept of a star with a quadrillion Gauss magnetic field, a star whose crust is cracking under unimaginable stress 50,000 light-years away, our own problems can shrink. They can be put into their proper cosmic perspective. They are very, very small. And that perspective is a gift. The universe is vast and ancient and powerful, and for the most part, completely indifferent to us. And that indifference is not a cause for fear, but a reason for calm. It means we are free to create our own meaning, to find our own peace in the small, warm, and precious bubble of our own lives on our own quiet planet. The story of the Magnetar is not our story, but knowing its story is happening out there in the silent dark makes our own story feel even more special. So let your mind be at ease. Let the quiet hum of the universe be your lullaby. Sweet dreams.